Good morning, afternoon as appropriate. My name is Andres Alzate, an environmental engineering student, and together with my colleague
Hello, my name is Brian Arcos. Nice to meet you.
and civil engineering student, we are going to present the topic of the hydraulic design of bridge, with emphasis on hydraulic clearance. The hydraulic design of bridge is a design process that through rigorous analysis allows us to define the interaction between the bridge structure and the water flow. This is essential when conducting studies to ensure the safety, functionality, and durability of the bridge over time. This process is fundamental to prevent flooding, avoid scoring processes that could affect the foundation, and ensure the efficient passage of flow beneath the structure, without obstruction or backwater effects that could endanger the infrastructure or its surrounding. Among the main hydraulic variables considered in this design are the expected maximum flow rate, the flow velocity, the slope, the type of bed, whether rocky, alluvial, or mixed, and the water level during events such as floods. One of the most important elements in the design is the hydraulic clearance. And what is it? The clearance in a bridge or viaduct refers to the height between the bottom of the beam and the riverbed in the case of crossings over rivers or streams. A very similar case applies to underpasses or routes, whether for vehicular or pedestrian traffic, where the clearance is the distance between the lowest point of the bottom of the beams and the highest point of the pavement of the route being crosses. In such underpasses, a minimum clearance of 5 meters is recommended. And why is it important? Hydraulic clearance is very important for bridge design, as it ensures that the water flow can pass freely beneath the structure, especially during flood seasons, without causing backwater effects or direct impacts on the bridge. The safety distance reduces the risk of damage caused by collisions with floating objects like logs or debris, improves the structural safety of the bridge, and reduces the risk of backwater effects and potential upstream flooding. What factors are considered to calculate it? First, the expected maximum flood level. For example, the level associated with a 100-year return period. An additional safety margin, which depends on regulations or technical judgment, and the characteristics of the riverbed, such as whether it's stable or prone to morphological change. What standards are used? In Colombia, INVIAS recommends a minimum clearance of 1 meter above the flood level from natural channels, although this may vary depending on the type of bridge and the importance of the route. Criteria from organizations such as HTO in the United States can also be considered, which suggest similar margins depending on the type of flow and structure. And finally, an example. This diagram illustrates the concept of hydraulic clearance in bridge design. It shows the vertical distance between the maximum water level, HW, during floods and the bottom of the bridge structure, known as the head beam. This clearance is essential to allow water and any floating debris to pass safely beneath the bridge without impacting the structure. The image also highlights other key components such as the natural and reinforced riverbed, embankment protection, and structural foundations. Proper slope design and foundation stability are critical to prevent erosions and ensure long-term durability of the bridge. On the other hand, the following image is a real-life example showing a river overflow or flood event, and its effects beneath a bridge. If the hydraulic clearance has not been taken into account, the current will likely have swept the bridge away.
I'm going to talk a bit about flow sections. Flow sections are a key part of hydraulic engineering. They allow water to pass safely beneath bridge, and their correct design is essential to prevent flooding and structural damage. In definition, a flow section is the part of a river or channel that flows under a bridge. It's designed to carry water through safely without compromising the bridge's structure or causing overflow. Types of flow sections. Common types include rectangular, trapezoidal, and irregular. Rectangular, easy to build but not always hydraulically efficient. And trapezoidal offers better stability and flow characteristics. And irregular, shaped by the natural river bed, often found in natural or semi-natural channels. Design criteria. Several factors are considered in flow section design. Hydraulic capacity to handle peak flows. Flow velocity, which must be balanced to avoid sediment buildup or erosion, and sediment and erosion control to preserve the structure and channel function. Importance of alignment with the natural channel. Aligning the section with the river's natural path is vital. Poor alignment can create turbulence, increase the risk of score near bridge foundations, and damage the structure over time. Calculating area and its role. The cross-sectional area is used in the flow equation, where Q is the flow rate, A is the area, and V is velocity. In most cases, we also apply Magning's equation to estimate velocity based on slope and roughness. Common design failures. Frequent problems include sections that are too small, leading to water overflow, bad alignment, which cause erosion or sediment accumulation, lack of erosion protection or poor sediment handling strategies. Good versus bad design example. A well-designed sections allow the smooth, uninterrupted flow and protects the bridge structure. A poor design might show signs of erosion, debris buildup, or even water bypassing the bridge entirely. In conclusion, designing flow sections with proper analysis and respect for natural river conditions is essential for the durability and safety of bridges structures.
Hydraulic design is crucial for bridge safety and environmental protection, and its success depends on the collaboration between civil and environmental engineering to achieve efficient and sustainable solutions.
Thanks for watching.